Kennedy.
How's it going, Paul? Or Dr. K?
Yes.
This is Jack.
Hey, Jack. I thought I was talking to Kennedy.
Yeah, her and I were talking, and she asked if I wanted to join. She gave me the information, if that's cool.
Yeah, sure.
Oh.
How did you feel about last night?
Pretty good.
Glad it's over?
Yeah.
Good.
How about you?
It's fine. It was odd, but you know.
Yeah.
We're hanging with it. Let me go get my annotated version of the article.
Okay.
Okay.
In the middle of working on something. Let me shut that down so I don't lose my work. All right. All right, you guys have questions about the literature summary?
Yeah. So, is the main idea just that females' time out was higher than males, which means that the males' PRR is higher than the females?
Yeah, so the more time you spend on parental care, in this case, the less time you have to acquire additional mates. And so that time that you're spending on parental care, they're referring to as time out. Time in is the time that you have available to seek out new mating opportunities. And so as a result of that, any time out that you have, because you're caring for tadpoles, you're producing infertile eggs to feed the tadpoles, you're moving the tadpoles from bromeliad to bromeliad. All of that time that is invested in those tadpoles is time that you're not able to invest in a new reproductive effort. So the more time out you have, the lower your potential reproductive rate is going to be, because you're spending all of that time and energy raising your current reproductive effort rather than investing in a new reproductive effort. So in this case, the females have a much greater amount of time that is spent time out than is spent time in, because of parental care in this particular system. This is not the case in all poison arrow frogs. In some poison arrow frogs, the males take up most of the parental care duties, and so the males have more time out than time in. And as a result, you would expect a different mating system to have evolved in that case. Does that make sense?
Yeah.
So yeah, that's a big part of it.
And so the PRR,
Mm-hmm.
It's the maximum number of independent offspring that the parent can produce per unit time,
Mm-hmm.
right? So what is that? That's just like the highest number that. What do they mean by per unit time? Like,
So it's a rate. How many offspring can you pop out per per week, per month, per whatever? So imagine. I think I showed you guys the Lucille Ball video where the candies are coming out on the conveyor belt, and her job is to wrap them up and put them in a box. And it starts out really slow, and that's because you're getting used to putting the candy wrappers on, and then the conveyor belt speeds up. And as the conveyor belt speeds up, you should, in theory, speed up your wrapping to match the speed of the conveyor belt. So over time, your rate of candies wrapped and put in boxes goes up over time. And so anytime you see any sort of rate, it's whatever the thing is, a rate of divided by time. How many candies do you get in the box per unit time? How many babies do you pop out as a poison arrow frog per unit time? So it's just whatever that unit of time is. It could be days, it could be weeks, it could be months. But the higher your rate is, the more you're putting out. So each individual who has the higher primary, so of the two sexes, if you have a higher potential reproductive rate, you're going to be competing for access to the reproductive resources of the member of your species that has the lower potential reproductive rate. So males can fertilize, can mate with, fertilize a lot of female eggs. Females can't do that because they're spending a lot of time with the eggs that they just produced, getting those up to metamorphosis. So male reproductive output in this case is limited by how many females they mate with. Female reproductive effort is limited by how much time they have to spend raising offspring. Those differences appear in these authors' measure of what they're calling timeout. And so in the introduction, it talks about how timeout and potential reproductive rate are inversely correlated with one another, inversely related with one another.
right?
That should make sense. What else?
I had my question was for the results. So Ken, if you had anything for the rest of the intro or methods, I'll let you go first before we move on.
No, I think that's fine. I mean, they used a lot of different, they talked about a lot of different analyses that they used for statistics,
Mm-hmm.
but I wasn't sure which ones were relative to their main conclusion of
Yeah, so
being.
go to table one. When I was talking to Alexis about this, table one confused her.
Yeah, that's what I was gonna. Both table 1 and 2 were a little confusing to me. I was gonna see if we
Okay,
could go through
so in table one, they did something weird. They they did something that I would have complained about had I been a reviewer on this paper. Um, they basically have a bunch of predictor variables, and they're trying to predict male mating success, which is the dependent variable. And they have calling activity, they have perch height, territory size, number of days present, snout vent length, and weight. And in the left-hand side of table one, they have basically taken all of those explanatory variables, the independent variables, and they've done a series of single what we call ordinary least squares regressions, where you basically have one predictor variable trying to explain one dependent variable. And they found that calling activity and perch height were both significant predictors of male mating success. The rest of these things are not significant predictors of male mating success. So you can see that in the section where they have the p-values for this. So calling activity and average perch height are significant predictors of male mating success. Then after they've done that, they run a multiple regression where they put all of these things into a multiple regression and say, okay, which of these things significantly contributes to male mating success? But they only found that calling activity was significant. And so the kind of multiple regression that they did is called stepwise regression. And what stepwise regression does is it enters the independent variables into the regression sequentially. So in this case, it would have put in calling activity would be the first variable that goes in because calling activity accounts for the most variation in the data. Then they would have put in the next most explanatory variable, which in this case would have been average perch height. But what they found was that after they had accounted for variation due to calling activity, the amount of additional variation that was explained by perch height was not significant. And so their multiple regression only had calling activity as a significant variable because none of the rest of these explain any more variation than calling activity does. And so why, when you do single regressions in the left-hand side of the table, is average perch height also significantly correlated? Well, the reason, but it doesn't appear in the multiple regression. Well, the reason for that is that probably calling activity and perch height are highly correlated with one another. So they're telling you basically the same information. And so whichever one of those explains the most variation in mating success is going to be the one that ends up being the one that prevails in the multiple regression. So it's a little confusing. It would have been less confusing if they had just done the multiple regression, which is the appropriate thing to do in the first place. Running a bunch of simple regressions and then running a multiple regression on the same data set doesn't make any sense statistically. So for my way of thinking, the multiple regression model is the thing that you need to pay attention to. Now, had they been a little more careful about what they were doing, they would have explained this in the results or the discussion, but they don't actually ever talk about any correlations between calling activity and perch height. I just know that that's probably what the case is, given that the multiple regression only includes one of those. Does that make sense?
Yeah, much more. So at what point in a single regression is something like important or correlated or like found to be significant? Like, is it above a certain level?
Well, it's gonna depend. Let me.
Oh, is it? Because it says I mean, like territory size had still a large or somewhat above 50.5 for the correlation coefficient.
That's the correlation coefficient. So let me go and get something for you that I can share with you. So it's funny, we just finished talking about this in my applied stats class. If you were in my applied stats class, you would not be asking me this question. So here's an example from my class. You have a bunch of data, and these data are basically relative humidity and, can you guys see my screen?
Yeah.
These data are the relative
humidity and weight loss.
And weight loss, yeah. So this is actually an example that we gave you back in evolutionary ecology. But basically, these are the weight loss of flower beetles under different conditions of relative humidity. the graph looks like this. And so it looks like the lower the relative humidity, the more you lose weight, the higher the relative humidity, the less weight you lose. And so what our regression is attempting to do is to find the best fit line through this cluster of points. And so we go through this process. So the grand mean, the average relative humidity is a little more than 50, and the average weight loss is 6.02. And if you were just looking at this as a single sample, you would see that the residual variation, the amount of variation that is the difference between the data point and the mean, is quite large. And that's because a horizontal line is a terrible fit of the data. A horizontal line does not describe this data set very well. And so the process of going and doing linear regression is you're trying to arrive at what is the equation that is of best fit. Well, it's the equation that reduces the residual variation around the line. So these are the residuals. You see in some cases they're quite small in the middle of the data set, but at the flanks of the data set, they're quite large. So this is the line of best fit, and you could see how the residuals would be much smaller if this were the line of fit rather than the horizontal line of fit. So you calculate these things using a bunch of equations that you learn about in applied statistics, which we're not going to go through. But this is what the line of best fit would look like. And you can see that these residual values, the distance between the data point and the line, are now very small compared to what they were when we had just a slope of 0. So any regression is testing whether or not this slope is different from a slope of 0. And we quantify this by basically finding two things. We look at what the sums of squares is due to regression and the sums of squares residual. Sums of squares due to regression is how much does the regression line account for variation in the response variable. So to what degree does, well, to what degree does this line explain variation in mass loss versus unexplained variation? And when you look at that, it goes into a regular kind of ANOVA table where you have sums of squares due to regression, sums of squares due to residual, and that's the sums of squares due to regression, sums of squares due to residual. Divide that by the degrees of freedom, that gives you the mean square. It gives you an F, which in this case is a monstrously large F, and that tells you whether or not your regression is significant. But what this regression is actually testing is this slope of best fit different from a slope of 0, or is it not different from a slope of 0? And in this case, it's different from a slope of 0, and the slope of this is a negative slope. And so the steeper the line is, the bigger the slope value is. And so in this case, the slope is actually quite close to 0. It's negative 0.053, which is estimated down here. But because the data around the line are really tightly correlated, so the slope of this line is 0.053. But because the data are so close to the line, it's really easy to calculate that that line is different from a slope of 0 because relative humidity is a very good predictor of mass loss. And so generally, the bigger the regression slope is, the easier it is to tell from 0. But there are situations where you can't really tell the slope different from 0 because the variability around the line is so high. So in some cases, it's really easy to see that this line has a slope of 1. That's not the slope value. The slope value is 1, what you multiply times the x variable. So this is a slope of 1 with an r square of 1. This is a slope of practically 1 with an r square of 0.907. So here the data are more scattered around the line. here the data are even more scattered around the line, and here the data are super scattered around the line. Well, as you get more and more scatter around the line of best fit, it becomes harder and harder to tell that regression slope from a slope of 0. So for example, these regression slopes are really, really shallow, and there's a lot of variation around the line, which makes it difficult for you to tell whether or not this slope is different from 0. Now, in this case, this person has hundreds of observations, and so he's kind of killed it with sample size, and so he's still able to detect that that slope is different from a horizontal slope. But these data are quite messy, and if he had only 30 data points and his data were this messy, he wouldn't be able to distinguish that. So there is a certain degree to which the size of the slope is important, but if the data are very variable around that slope, it's almost impossible to tell that that slope is different from a slope of 0. So yes, to a certain degree, in table 1, the left-hand panel, the bigger the number, the more likely you are to see a significant correlation, but it all depends on how variable the data are around it.
Gotcha.
And you see that the correlation coefficient that is 0.52 is very close to significant, but doesn't quite meet the threshold. And as they go down to 0.18 and 0.06, the p-values are higher and higher. Well, it's because those correlation coefficients are getting closer and closer to 0. And as they get closer to 0, it's harder to distinguish them from 0. Any other questions about table 1?
Nope. Nope.
Okay, Jack, you had questions about table 2.
Yeah, so you seem to do a good job of explaining table 1, and I kind of understood that like they were measuring these different variables for table 1, but the big thing was that like I didn't understand the correlational coefficient values.
Okay. Yep.
So likewise here, I don't understand the variation in numbers and like necessarily what they mean relative to everything else. Because I understand the variables of mean of male mating success, variance of mating success, and stuff like that, but I don't know.
Okay, so this goes back to in their method at the very beginning, at the very end of their methods. Yeah, the last paragraph in the methods, the calculation for the opportunity for sexual selection on male reproductive success followed the modification by Klug of models developed by Wade and Arnold. So Mike Wade and Steve Arnold back in the early 1980s wrote a series of papers that both handled kind of the theoretical issues about measuring natural and sexual selection in populations, as well as the practical issues involved in actually going out into nature and doing this. And this was one of the early papers that they're citing here, where they wanted to look at the opportunity for sexual selection. So the opportunity for sexual selection is I sub S. And it's the variance in male mating success divided by the square mean of the male mating success. And so if every male in a population, so think about a population of frogs out there, if every male is having the same reproductive success, every male mates with one female, each female puts out 4 tadpoles, all males are getting the same mating success. So the variance in mating success is not very high, because I should have saved this when I was going through this with Alexis, because I did all these calculations with her the other day. Oh, maybe I did. Maybe I did save these things. So give me a minute to write something down.
Okay.
Nine times four is 36, right?
Correct.
All right. I just did a lot of math here in a hurry. So in that formula, in those formulas on in table 2, one of these formulas is the average mating success. And so in this case, the average mating success was 3.14. And then you have the variance of male mating success, which is 17.36. So can you guys see what? Can you guys see this clearly?
Yeah. Now that you're, yep.
Okay, so on this side right here, you can
Yep.
see that male mating success, every male, so there are 5 males in this population. Every mating
Okay.
success, every male achieves a mating success of 4 offspring. So when you calculate the mean, you just add up each male's mating success and you divide that total by the number of males. So you have 5 males, each one gets 4 offspring, so you have 20 offspring total divided by the 5 males. So your average is 4 because that's what everybody's getting. The variance is calculated as the difference between each individual male's success minus the mean squared divided by 1 minus the number of males that you have. So in this case, since the mean is 4 and the mating success is 4, 4 minus 4 squared is 0, 4 minus 4 squared is 0, 4 minus 4 squared is 0. This adds up to 0. There's 0 variance. All of these males are achieving the same amount of success. And as a result, the variance estimate, S squared, is 0. In this scenario over here, though, one male is having 16 offspring, and all of the other males are having 1 offspring each. This still adds up to 20. 20 divided by 5 is still 4. So the average success is 4. But there's a lot more variation, because when we subtract 4 from the observation, that ends up being 12. And then for all of the rest of them, it's a -3. 12 squared is 144. 3 squared is 9. That thing sums to 180. 180 divided by 4 is now a variance of 45. So anytime males vary a lot in their reproductive output, that's usually going to lead to sexual selection occurring, because somewhere one male is getting all of the reproductive opportunities, and all of the other males are not. That's either because that one male who's getting all the reproductive activity, all the reproductive opportunities, is a superior competitor compared to these other males at gaining access to females, or there's a lot of female choice going on such that all the females are choosing to mate with this one male rather than these other males. So whether it's due to male-male competition or whether it's due to female choice in choosing a single male to mate with, the opportunity for sexual selection is high here. The opportunity for sexual selection is not very high here, because males are either all equally competitive for access to females, or females are not being very choosy. In both of those cases, you have a lack of sexual selection here. So when you go back to the paper, you see that the variance in male mating success is 17.36. That's quite high. So the intensity of sexual selection is the variance divided by the mean squared. So if you square 3.14, and we can do this on our little calculators. Let me find a calculator. So 3.14 squared. 3.14 squared is 9.8596. 9.8596. Wait a minute. Is that right? Yeah, so 3.14 is the mean. When we square that, that is 9.856. And we divide that into whatever the variance was, which was 17.36 or something like that, right?
Mm-hmm.
Yeah, 17.36. So if you divide 17.36 by 17.36 divided by 9.8596, that should give you whatever that value is that they have there as the opportunity for sexual selection, 1.76. So actually, I need to do all of this, not on my iPad, because I can't flip back and forth between screens and calculator, and I can't remember all the numbers.
It's the couch.
It is the couch. Oh yeah, I've talked to you guys about the couch, haven't I?
Yeah.
So let me actually make myself a spreadsheet. Okay, time to share screen. So it's just easier for me to do it this way for you. So mean mating success is here, 3.14. Variance in male mating success is right here. And they would have calculated male mating success the way I just did it for you. So the scenario that I just did for you so I'm going to just build two scenarios for you right here. So we have 1, 2, 3, 4, 5 males. Each male does 4 offspring apiece. The average is just the average of these mating successes. Here we had 16, 1, 1, 1, and 1. And so the average here is the same. Okay, so this is mean mating success of the males in both scenarios. So they both have the same mean, but here the variance is calculated as equals the sum of the individual value minus the mean, which in this case is 4 squared. And those all end up being 0. That thing sums to 0. And when you divide that sum by 1 minus the total sample size, which is 4, you get 0. Here you do the same calculation, equals this value minus 4 squared. Do that for all of these values, sum that up, divide that sum by 1 minus the sample size, which is 4, and you get a variance. So this is S squared. This is the variance of male mating success. And so even though the average mating success is the same in the two populations, the variation in mating success is much higher in the high sexual selection scenario than the low sexual selection scenario. So the way Arnold and Wade advocate measuring this is by basically the opportunity for sexual selection is essentially the variance in mating success divided by the mean mating success squared. And when you do that, you find that it is 1.76. So that's basically the calculation. The higher this number is, the more likely you are to have sexual selection occurring, because the bigger that number is, it means the more variation there is between males in terms of their mating success. And so that's technically how they're calculating it. And so you can generate those numbers from the table itself. Does that make sense?
So,
Is 1.76 a fairly high number then?
Yeah, sure. Because you've squared the mean. And so one of the problems with variation is oftentimes variance is correlated with the mean. And so one of the ways in which you can correct for that is dividing some measure of variation by the mean. So the last thing in this table, which is the coefficient of variation, is also a way of fixing, of correcting variation for the mean. So adding things to this spreadsheet that I've made for you. So the coefficient of variation here, they're reporting is 132.6. Well, the coefficient of variation, the equation for that is actually the standard deviation divided by the mean. Now, in this case, we can calculate what that is because we know what the mean, we know what the variance in reproductive success is. So the standard deviation is just the square root of the variance. So we can calculate the square root of the variance right here. That's 4.16. And we know what the mean is. And so the coefficient of variation is then going to be equal to the standard deviation divided by mean mating success. Times 100. I always forget to multiply it times 100. And so you'll see that that equals 132.6. Once again, this is a measure of the variation in a data set that is then comparable across a wide variety of scenarios because oftentimes as the mean increases, so does the variance. So let me go to something that you're going to hate me once again because I seem to do this a lot in this class. But way back in your first semester, we did a lecture for you on analysis of variance and coefficient of variation because in the VNet et al. Paper, the paper that was focused on Kanza Prairie, they calculated the coefficient of variation. And at the very end of this PowerPoint, which you saw at some point, so here we are at Kanza Prairie.
Your slide's still in Excel.
Oh, my slide's still in Excel. Oh, yeah. Let me share my general screen. So somewhere back in your evolutionary past of your education, we taught you about analysis of variance and the coefficient of variation. This was in the context of Kanza. So here are the figures explaining to you what was going on in Kanza. And just read this slide for a minute. Pay special attention to the elephant and mouse example. So if you want to know about the variation in a variable, tail length in this case, you can't really compare elephants and mice because an elephant's tail is much longer than a mouse's tail, such that the amount of variation from one elephant's tail to the next elephant's tail is going to be much greater than the total length of the mouse's tail, or for that matter, the mouse itself. So the coefficient of variation gives us an estimate of variation expressed as a percentage of the mean that is independent of the original unit of measurement. And you can see on the next slide that the calculation for the coefficient of variation is the standard deviation divided by the mean times 100, which is exactly what I just did for you right there. The standard deviation, which I calculated here, standard deviation divided by the mean multiplied times 100, and that actually happens to be exactly what they have in table 2. So it's just a scale independent measure of variation. So
is table 2 just basically showing us that there's a significant amount of variation?
yes, and that significant amount of variation in male mating success is what creates the opportunity for sexual selection to occur. And in this case, the sexual selection, is it due to females being choosy, or is it due to males competing with one another for access to females?
I'm not sure.
They talk about these things in the discussion. And they also talk about these things in the results, actually. As a matter of fact, right below table 2, they talk about one of these things in the paragraph right below table 2.
Is it being choosy?
So in this case, males appear to be choosy because on only 2 occasions did the male stop calling before during courtship, but females broke it off with males 11 different times, and so it appears that females are more choosy than males. What else? What else from this paper tells you about male-male competition versus female choice?
They talk about the males defending their territories.
Males are defending their territories. One of the primary indicators of male mating success is calling intensity, calling activity. Uh, Calling activity is essentially a male advertising to females that he's there, and males compete for access to the sonic landscape by calling a lot. If you want to outcompete your male competitors, you have to call louder, you have to call longer, you have to call when they're calling as well as calling when they're not. And so in this case, is sexual selection being driven by female choice or by male-male competition?
Well, yeah, since calling activity was significant in table 1, wouldn't it be or male-male competition?
But also,
Both, yeah.
it would actually be both. Males are being choosy, and females are being choosy, and males are competing with one another for access to females. So in this case, sexual selection is being driven by both of those things simultaneously. And that's indicative. That's just goes right along with what is in table 2.
Mm-hmm.
Those are the kinds of numbers that you would expect in a situation where sexual selection is happening, because variation in male mating success is due to variation in male mating success is 132% of the mean, and so there is a lot of variation in male mating success. So that's what table 2 is about.
So in their hypotheses, they like their second hypothesis is that because of the lowered female PRR, that means that they're more selective, and so their female choice leads to variance in mating success in polygyny and successful males. And so then it just says finally, male to territorial behavior is related to competition for access to females. So
Sure.
do they not relate that the competition for access to females is also leading to that variance, or
Oh no,
what?
I think they're saying that those are all involved.
Okay.
The way I read it.
Okay.
Um, so for time in and time out,
Yep.
did they? I read this 2 days ago, so and I have only had the opportunity to read through it once. I could be remembering incorrectly, but did they just straight up just do some calculations to try to find time out? Like I feel like they would have done some table or graphical use of.
It's actually in the text. So
Right, Jack, right above the start of the discussion.
Yeah, I see it. It's like the 2 times 1.5 hour matings plus 3 hour tadpole transport. It's just I didn't know if like they strictly just did all females and then average them and all males and then average them, or what.
Yeah, so this is kind of a theoretical sort of thing. So, for example, it takes 8 days to produce eggs, an hour and a half for matings. You need 2 matings to produce. Let's see. Let's see. The average clutch size was 4.6 eggs. So we conclude that the production of 1 egg takes approximately 1 day. Mean duration of tadpole transport to water-filled bromeliads was 3 hours. So they're in the big paragraph above where the female timeout is being calculated. They're calculating all of these things. Actually, parental investment, this whole section is them arriving at these calculations. So there's 8 days of egg production, 2 times 1.5 hours of matings, 3 hours of tadpole transport, and 22 days of tadpole rearing. And so they came to 30 days plus 6 hours. But if you look at 30 days plus 6 hours, that doesn't actually equal 366 hours, because they only calculated 5 hours for the males, and so they then scaled everything to hours. But what you have to do is 30 hours plus, or 30 days plus 6 hours. If we do, well, let's go back. Let me
726, right?
Yeah, let me go back and share my screen again, so we can do these calculations in Excel. So if we had 30 days and 6 hours, 30 times 24 is 720, which would make 726 hours the female timeout. But what you don't recognize is that these frogs are diurnal. And so what they did was they used 12 hours. Since they're in the tropics, you have approximately 12-12-hour days, 12-12 light period. And if you change this to 12, that is 360, and 360 plus 6 is where they get the 366 value.
Okay.
Yeah, so it's just, they're just calculating how much time does it take to do all of these things relating to mating and relating to rearing offspring. Who's doing which of them? Is it males or is it females? And that basically means that males spend about 5 hours timeout in activities caring for offspring. Females spend 366 hours in timeout caring for offspring. And that disparity in timeout accounts for this disparity in potential reproductive rate. So Alexis had the same question, like, that doesn't add up. And I'm like, it adds up if you consider a 12-hour day rather than a 24-hour day.
Gotcha. Okay. Thank you.
What else?
I think that's all I had.
Yeah, I mean, I think I have a good idea of what needs to. At first, I was kind of struggling as to, like, here's these hypotheses, but there's a lot of different things that they're talking about in the results. So I think I have a better idea now of what.
It's like everything else, distill it down to what its essential things are.
Yeah.
In this situation, you have males setting up territories, calling, things like that, and that's generally going to be a sign of male-male competition. Why would males be competing? Well, males are competing to the limited resource. What is the limited, or competing for the limited resource? What is the limited resource? It's access to females. Females are the limiting resource in terms of reproduction. As a result of that, they're being competed for through male-male competition. But because there's a lot of competition for those resources, it also puts females kind of in the driver's seat, and that they can be choosy about which males that they are going to mate with. And so you see that there is variation in male mating success, both from table 2, but also from the information in the last paragraph of the results, just above parental investment and calculation of timeout. One of the most successful males mated with at least 5 different females, while females mated with 1 to 3 males. Once again, females mating with fewer males than males mating with females. But then also at the very beginning of the results, where it's talking about the males in the first couple of paragraphs of the results, The most successful males mated 12 times. The other males mated between 0 and 5 times. So once again, this is in the second column on page 217 under differences in male traits, mating, and reproductive success. So a couple of males were getting most of the matings, and all of the rest of the males were getting relatively few matings. Once again, variation in male mating success means that females are being choosy. They're choosing only certain males to mate with, and the males that they're choosing are probably the males that have fallen out as the victors in these male-male competitions for territories. So bust it down to its essentials. Male-male competition, female choice. Are these two things happening? Yes, they are.
Yep.
Got it.
And then for the my last question is just basically for the last part, the like creating part.
Mm-hmm.
The last, like one of the last paragraphs basically says, long-term research would be an essential complement kind of thing, and then they talk a little bit about why. Like, can we use that?
You can, but actually there's something that's actually more interesting to me than that. That's not what I would have finished up with in this discussion if I was writing this paper.
Are you more?
They also talked about like how there's other factors involved
Yep.
that could affect PRR, but they don't talk about them or they didn't analyze them. The temperature, food, and nest site availability.
Yeah. So
Yeah, I
so
was just thinking that same thing.
presumably, if you're a male and you're setting up a territory, that territory hopefully has things that are of use to a female. Otherwise, why would she be attracted to you because you hold that territory? Now, we know that in lek systems that the territory that the male obtains and maintains doesn't have seemingly any resources of use to the female, but that's not necessarily the case with these frogs. And so one avenue of future research would be to assess, okay, well, these males are in these territories. What are in these territories that contribute to mating success other than just attracting a female? But there's other things that you could also think about. In the first big paragraph on the right-hand column of 219,
The sequential and simultaneous polygamy.
no,
That one.
further down.
Oh, are you talking about the males that were still defending their territory?
Where are you at?
You said right-hand column on 219, right?
Right-hand column 219, halfway through that first big paragraph.
Oh, okay. Sorry, I didn't hear the halfway first.
And I mentioned it towards the beginning of our chat today.
Oh, the male and parental care.
Yeah, so within this family of frogs, so remember that whenever you're making comparisons, we talked about this at the very end of the mating systems. One of the ways that you can look at mating systems is looking across broad phylogenetic spans. So, comparing what happens in one family of frogs with what happens in another family of frogs. But another way that you can look at things is look at, for example, different species within a family and say, okay, in the family Dendrobatidae, there are systems where there's male parental care only, there's female parental care only, there is biparental care. You could then take this same kind of study that was done in this paper, looking at what the investments of males and females are in terms of how much time they're investing in reproduction, i.e., what is their time out, what is their their potential reproductive rate, and their operational sex ratio, and then using those values to basically ask, are those values in keeping with what you observe in terms of the mating system? And in this case, it's been done in a place where, in a species where sexual selection is high. Most of the parental care is done by the female. Very little parental care is done by the male. And as a result, you have male-male competition for access to females and females that are choosy. What are all of those variables like in a situation where the male seems to do the bulk of the parental care? Well, you can find examples of dendrobatid frogs, frogs in the same family, where males do the bulk of the parental care. And you can also find biparental care systems. Well, do these same ideas play out in ways predicted by timeout and potential reproductive rate? Are those ideas, timeout and potential reproductive rate, useful in explaining male parental care, biparental care in the same group of frogs? For me, that would be the more intriguing thing to do. But that's just me. So that's the nice thing about the next steps. There are multiple next steps, all of which have value. For me, that's the next step that seems most interesting. But that's just where my interests lie.
Yeah.
Like Kennedy asked earlier, are we allowed to kind of go off of some of their next steps like this?
Sure, I wouldn't rip them off wholesale, but you could certainly use that as a jumping off point.
Okay.
Awesome. Thank you.
Because
thank you.
the thing that I just gave you is something that they're mentioning. They're not exploring it particularly deeply. So yeah, that's appropriate.
Okay. Cool.
All right.
Thanks for the help.
I'll talk to you guys tomorrow.
Will you please post this on the YouTube?
This video?
Mm-hmm.
Sure, I can do that. I have a meeting with another student coming up, so it'll probably take me about an hour to get to it, but sure.
That's okay. Yeah.
All
Thank you.
Thanks. Bye.